So the question is, if you, like in the case of metals, if you introduce different elements into the crystal, the question is what happens then? So in the metals, the situation was relatively simple. You would simply replace one atom with another. In the case of the ionic crystal, again, because of the charge neutrality requirement, there might be other associated defects that are introduced. So an example would be potassium chloride, in which we will introduce calcium chloride. So you can simply think that you mix two compounds together. So, for example, you start with potassium chloride, and then you add calcium chloride. And this, in this particular case, this would be the potassium, this would be chloride atom. And because calcium atom is 2+, it actually changes or substitutes two potassium atoms, right? So if I introduce one calcium, it is equivalent to two potassium atoms. So I have to think about, if I replace one of these potassium atoms, what does that effectively mean, right? So what that means is that I'm forming a vacancy. So again, if this was my calcium 2+, I have to form a vacancy of potassium. So this will be potassium vacancy because calcium carries two positive charges in comparison to the potassium one. So how would I write this is that I would simply write that what I'm forming is a defect, which is the substitutional calcium that substitutes the potassium, and I'm forming one vacancy of potassium. Is that clear? Again, the idea is that at the end you have to, the charge neutrality has to be preserved in the crystal, so you're trying to figure out what are the different combinations that can give you that. Another example is if you have, for example, anion impurity. So for example, if you are adding oxygen into potassium chloride, again, because oxygen carries two negative charges and each chlorine atom carries one, I have to form, so if this was the oxygen, I have to form a vacancy, which is an anion vacancy. And how would I form that? How would I write this? So oxygen is replacing one chlorine atom and carries the charge, plus the vacancy that carries the opposite charge. Okay? So again, depending what are the compounds that you're mixing, you have to understand what is really happening at the atomic level. One thing to notice is that if you have a particular combination of the materials, there is no one prescribed way. So there might be multiple types of interactions that can happen. For example, we here introduce calcium chloride to potassium chloride, and I gave you just one example of the reaction that happens. But this is not necessarily the unique way how this can happen. So for example, this calcium, instead of replacing one potassium, can form interstitial point defects, etc. So I will just give you a couple of examples. So this is, again, we are adding calcium chloride to potassium chloride, and there will be two specific reactions that can describe the situation. And how we would write this is that we are adding calcium chloride into potassium chloride. And again, this will result in calcium replacing potassium atom, plus forming one of the vacancies of the potassium and forming two substitutional chlorine atoms here. So what is the meaning of this, the last part? Yes? Excuse me?
You're balancing mass as well as charge.
That's right. So you're simply taking, so whatever is on the left-hand side, it has to end up on the right-hand side. What I'm simply saying is that some of the chlorine atoms from this particular compound are ending up in the compound, and they're replacing the identical atoms, and the charge remains the same, right? So it's just a substitutional chlorine in a chlorine site, right? And it does not change the charge neutrality. So another type of equation or another type of a reaction that can happen in this particular case is that I can form an interstitial calcium which will carry two charges, and it will then as a consequence form two vacancies, potassium vacancies. Again, it has to be two because I'm balancing two of these charges, and I'm forming two identical substitutional chlorine atoms with no net charge. Okay, so what this tells you is that, again, if I mix calcium chloride and potassium chloride, there are different types of defects that can happen. They can happen simultaneously. Some of them can be happening exclusively at certain conditions. But how you determine which one is changing is simply, for example, by measuring density. How would the density influence the measurement? So how would you, for example, from the density measurement, determine which of these processes is happening? So in the first case, you're substituting one of the potassium atoms with calcium atoms. In the second case, you're introducing one substitute or interstitial, right? And then you have to simply calculate what is the difference in the masses of the corresponding ions on the right-hand side, right? So you simply know what is the mass of one ion and how many of them you are removing and how many of them are adding. Right? So for all of these combinations and reactions, you can actually calculate this, and from the density measurements and the spectroscopy, you can measure that. Yes?
Is it necessary to write that chlorine is replacing chlorine?
That's somehow assumed, but again, you're saying that you're adding something, so it has to end up somewhere. Okay? So this is just to tell you that, well, you're adding this compound, you're mixing it with potassium chloride, and this is the reaction that happens. If you were simply to write that you're introducing this calcium ion into the compound, then you would not necessarily have to write that. Okay, so again, different types of spectroscopic measurements can be done because different types of defects can give you different signature. Again, in ionic crystals, we mentioned that the defects can be both intrinsic and they can be extrinsic. Again, in intrinsic case, we were talking about Frankel and Schottky defects. So this is simply the case of the defects that are formed by the ions that already exist in the crystal. Extrinsic ones would be dopants and different type of impurities, like in the case when you add calcium chloride to potassium chloride. So the question, why is that important? So it's important because the intrinsic type of defects are governed by the thermodynamics. So we mentioned that, for example, the concentration of the intrinsic types of defects will be the exponential function that depends on the energy that is required to form that intrinsic type of defect over kT. Right? And again, what these intrinsic type of defects can be, these can be interstitials, they can be vacancies, they can be combinations of Frankel, Schottky, etc. So each of these defects will have an associated energy that is required for that, and you can calculate that. But they all have the same, this Arrhenius type of behavior. They're all dependent on the temperature, and you can, in principle, predict them. So if you, for example, plot a graph which will tell you what is the density of these defects as a function of 1 over T, this would be a typical Arrhenius plot, where you would have this line that is represented by the red line here. So this is governed simply, we know the crystal, we know the energy, and we can calculate this and measure that. But if you introduce another type of a material, so let's say that you have a certain concentration of impurities. In this particular case, again, we are looking at the calcium chloride and potassium chloride. There's a set concentration, right? So this is simply governed by how much of that material you introduce in the crystal itself, and this would be this flat function here. So what that tells you is that at room temperature, so the room temperature, so this would roughly correspond to 680 degrees. So the room temperature would be somewhere on the right-hand side. So what that means is that at room temperature, the behavior of this compound is driven by the impurities that we introduced, right? At high temperatures, this is purely driven by the intrinsic type of defects. So if you're thinking about an application that has to work at room temperature, it's very likely that these properties would be driven by the impurities that you're introducing in the material. If you're thinking about high temperature applications, then you have to think about what are the intrinsic type of defects. Okay? So again, in different regimes of the temperatures, properties are driven by completely different sets of defects. Okay? One is driven by thermodynamics, the other is by processing and how much of the material you introduce. There is another type of defects and another interesting type of defects that are present in ionic crystals, and it's called F-centers, and they're very interesting because they give different colors to ionic crystals. Very famous on nitrogen centers in diamond. And how these defects, these are point defects that are, so this particular vacancy here is filled by an electron, And because of very localized electronic states that are formed here, this will change the color of the crystal itself. So there are many crystals that you can find in nature, diamond crystals, for example, that are not transparent and shiny, that have colors. And the reason why this color comes is actually from impurities that are introduced in the diamond itself. So this is just a side note, but again, there are many applications where this is observed, etc. Another important point where these defects become extremely important are in semiconductors. So again, if you look into a transistor that you have in your phone or in your computer, it will be likely composed from silicon, intrinsic silicon or p-type silicon that has regions of heavily doped N plus material. What that simply means is that you have material that is p-type, and there are certain regions of the material that have completely different types of impurities. So I will just briefly tell you what P and N type means, and then we will learn about how we can introduce these types of defects. But the idea is that you have to have a very well-defined crystal. So you produce as pure silicon crystal as possible, and then in a very localized region of the crystal, you have to introduce different types of defects. So P and N-type doping is simply governed by the fact that you can replace some of the silicon atoms. So silicon is from group 4 of the periodic table. So if you introduce an element or an atom that is from group 5, for example, phosphorus, this will produce N type of a conductor. What that means is that simply you're replacing one of the silicon atoms. And because phosphorus atom has an extra electron, there will be one that will contribute to the conductivity of this particular crystal if you apply an electric field. In other words, if you have a pure silicon, there will be electrons and holes that are formed when you apply a bias or electrical field. The electron will travel in one direction and the corresponding hole will travel in the opposite direction. However, if you have extra electrons, then the conductivity of this particular material will be enhanced, and this will be called an N-type conductor because the conductivity is carried by the electrons, not holes. And the opposite thing happens when you add, for example, boron, which is from group 3. This will result in a P-type of a material. So in other words, if you take a pure silicon, you can make it either N or P-type, depending on what kind of impurities, in this particular case, substitutional atoms you make. Okay? So again, when we come back to this picture, what that means is that in this crystal here, I have one types of dopants, substitutional atoms, and then I have completely different types of substitutional atoms that are introduced very locally